When people talk about disruptive future technologies, something that comes up almost every time is quantum computing. With governments and companies pouring billions into the development of quantum computers, there seems to be a lot of potential in the idea. But what exactly is a quantum computer? And why is everybody so excited about it? To understand what makes a quantum computer different from a regular computer, it helps to first know what we mean when we say computer. In 1936, Alan Turing, who is by many considered the father of computer science, proposed a concept that would be later known as a Turing machine. The machine consists of a head and a tape. The head can move left and right on the tape and can read symbols that are written on said tape as well as write new symbols. The next action that the head will take is determined according to a table of rules that will take the symbol that was read and the current state of the head into account. This arrangement is then theoretically able to execute any arbitrary computer algorithm. This concept can help us determine what components are actually needed to construct a computer. To replace the head, we need a processing unit that is able to read and write data and combine it according to a definitive set of rules. In a modern computer, this would be the CPU with a respective instruction set, for example x86, ARM or RISC-V. To represent the state of the head, the CPU needs to possess a form of memory. In a regular computer, these are the registers. And finally, there needs to be some memory that the CPU can read from and write to, which in a PC is usually comprised of cache, RAM, and a hard drive or SSD. In what way is this now different in a quantum computer? Regular computers are based on classical physics, in most practical cases on electrical signals that are interpreted as discrete bits that can take the values 0 or 1 and that are combined using Boolean logic. As the name suggests, quantum computers are based on quantum mechanics, which is an entirely different model of the physical world. The fundamental unit of memory for a quantum computer is the qubit. These are combined using quantum logic. To understand the principles of quantum logic, one needs to grasp the fundamental principles of quantum mechanics. While classical physics works really well to model the macroscopic world, it fails to explain a lot of observations that can be made on the scale of atoms and subatomic particles. There are some key concepts that differentiate quantum mechanics from the way we usually see the world. The most important ones are the wave-particle dualism, superposition, the destructive nature of measurement, and quantum entanglement. The wave-particle dualism describes the fact that quantum objects sometimes behave as a wave and sometimes as a particle. This can be observed in a simple experiment that is called the double-slit experiment. When a coherent wave, for example a laser beam, hits two slits, they afterwards act as two independent radial wave emitters. When waves overlap, they interfere with each other. This creates an interference pattern on the screen. When the laser is now replaced with a particle beam of electrons or ions, one would expect two distinct places where the majority of the particles hit the screen, as we would observe when dealing with macroscopic objects. But instead, a similar interference pattern appears. This suggests that particles actually behave like waves in this case. Subsequently, the particle emitter is configured in such a way that it actually only emits a single particle at a time. In this case, one would expect to observe only two maxima, since there is seemingly nothing that a single particle can interfere with. But again, the interference pattern appears. This can only be explained if the particle interferes with itself. The particle seems to pass through both slits at the same time. In quantum mechanics, this is called a superposition, and the probabilities for each possible observable position or state can be described using a wave function. If we, however, position a detector at the slits to measure which of the slits the particle passes through, we can only ever detect the particle passing through one of the slits. At the same time, the interference pattern disappears. This tells us that the act of measuring actually changes the state of a quantum object. In quantum mechanics, one says that the wave function collapses upon measurement, and the measurement therefore destroys some of the properties and information that the quantum object carried beforehand. The final principle of quantum mechanics that is fundamental for quantum computing is called entanglement. When two quantum objects originate, for example, from the same atom, their states are not entirely independent from each other, but are instead correlated. Perhaps surprisingly, this correlation persists even if the objects are physically distant from each other. In effect, the information of a quantum system does not only consist of the states of the individual quantum objects, but also of the way that these states are entangled with each other. A quantum computer uses all these effects. The memory that replaces the state of the head in the Turing machine consists of the state of quantum objects that are in a superposition of the 1 and the 0 state. These are called qubits or quantum bits. A qubit is therefore always both 0 and 1 at the same time, but will take each of these values with a certain probability when measured. These probabilities are however not sufficient to fully describe the state of a qubit. We also need to consider in what way the qubit is entangled with other qubits. This is why the Bloch sphere is a popular way of representing qubits. A pointer within the sphere can give us all the information we need. The y direction tells us the probabilities of the bit being measured as 0 or 1. The x and z directions are then free to encode the entanglement. Physically, a qubit can be implemented in different ways. One popular approach is an ion trap. An atom that has an electrical charge is called an ion. This means that the ion can be manipulated using electromagnetic fields. The ion can therefore be trapped using an appropriate configuration of fields. Other approaches involve using photons as quantum objects or employing superconducting loops. All of the approaches have advantages and disadvantages, and to this point it is unclear which one is the most promising for building a commercially viable quantum computer. The way a qubit is physically realized also has influence on how the bits are manipulated and combined. For ion traps, this usually means using photons of a given quantized state to influence the ions. The head itself is replaced with a quantum processing unit that combine the qubits with each other. The rules that apply to combining and manipulating qubits are different from the Boolean logic used in regular computers. However, operations can be represented as quantum logic gates, similar to the logic gates of Boolean logic. The application of a gate is then equivalent to a rotation of the pointer on the Bloch sphere of the affected qubit or qubits. Popular gates include the CNOT or controlled NOT gate and the Hadamard gate. Generally, quantum logic gates are reversible. That means applying the inverse of a gate after the gate itself was applied will always yield the original state of the qubit. The measurement of a state, however, is not reversible, which means that when the bit is measured, part of its information is destroyed in the process. This obviously creates a problem for reading the result of a calculation. One way to deal with that is to perform the calculation multiple times and to statistically interpret the results. This is often done in practice, although there are other approaches like the quantum Fourier transform. While it would make sense to also have data in program memory that consists of quantum objects, these are currently too technically expensive to implement. This means that the memory replacing the tape of the Turing machine is still comprised of regular memory. A control chip is used to create an interface between the regular components and the quantum processor. One possible chip is, for example, the Intel Horse Ridge 2 cryogenic quantum control chip. To summarize, a quantum computer is a computer where the state memory consists of qubits that are in a superposition of 0 and 1 and could, for example, be implemented using ion traps. The qubits are combined using quantum logic gates, which creates a unique instruction set for quantum processors that is distinct from any that can be used for regular computers. An algorithm that is based on quantum logic is called a quantum algorithm. While quantum algorithms are functionally equivalent with regular algorithms, meaning that any algorithm can at least theoretically be translated to a quantum algorithm, some quantum algorithms have significantly lower time complexity than their regular counterparts. This results in a difference of the feasibility of certain calculations. This is called the quantum advantage or quantum supremacy. Currently, there are no quantum computers that can execute any economically relevant problems faster than classical computers. It is believed that with a quantum computer that is sufficiently powerful, big advances can be made in the fields of cryptography, simulation, data science, and machine learning. This is, however, not yet commercially viable with the available hardware. The currently available quantum hardware is primarily used in research. The version of a quantum computer that is most popular at the moment is built by IBM. The current Osprey QPU has 433 qubits based on superconducting semiconductors. The main difficulty with creating large-scale quantum computers is decoherence or instability of the quantum state of the qubits. To create stable qubits, the environmental conditions must be closely controlled by cooling the system to very near absolute zero, creating a near-complete vacuum. This is obviously very expensive and makes it difficult to miniaturize the elements for scaling up. Quantum computers are a very interesting and promising emerging technology whose true implications, however, still remain to be seen. While there are major improvements that are made at the moment, there are also big obstacles in the way of creating quantum computers that provide a usable advantage over classical computers.